Are we good for starting?
Yeah, I just pressed the start recording.
Oh, great. Perfect.
Means we can start. I'm gonna go up. I'm gonna move my mic so you don't hear my heavy breathing. But go ahead. I'm online.
All right. Hi, everyone. We're here today to be talking about Monte Carlo methods, and this presentation is really going to cover Monte Carlo methods on a very, very high level, almost strategic basis. And the reason for this is because Monte Carlo methods are very, very complicated, and it takes a lot of mathematical skill and just grit to be able to work through them and actually understand how they work and how to build them yourself. And unfortunately, webinars are just not a really good place to learn that kind of stuff. It's really just sort of trial and error and a lot of reading to do. And from your perspective, it really wouldn't be beneficial of me just to open up an R session and start typing code and showing you all these numbers flashing around. You're really not going to learn much out of it. This presentation is really to help you if someone comes to you and says, hey, I have this Monte Carlo model, you can really understand how to approach something like that and figure out, well, what exactly you would want to do with it and what things to be aware of when you're thinking about it. Are there any questions? And by the way, you can address them in the type line, and if we have a lot of commentary, then we'll unmute everyone so that we can have a bit more of a lively discussion. But are there any questions before we begin?
Yeah, everyone could just chat away on the chat box. We'll take them, I guess, in chunks, what we normally do. Guess nothing. Actually, Andrew was asking about Monty Python methods. Response?
Actually, you know, that sounds like a great topic for another webinar. I'm more than willing to hear it from you, Andrew. That actually sounds like a lot of fun. You can incorporate it with dancing somehow. That would be even better. And by the funny. By the way, this picture, just one thing about Monte Carlo methods before we begin. They're absolutely beautiful. You can just do on a pure. I'm not sure what I'm hearing. Are you guys hearing that?
Yeah, I'm trying to get on it. Steve, if you can mute yourself.
Joseph here. I think it's Joseph. He's not.
Joseph, or everybody. If everybody can mute themselves.
No, I think it's Joseph.
Okay. Yep, I got him. Okay, there you go.
Yep. So, all right. As I was mentioning, Monte Carlo methods, they're just on an aesthetic basis. They're absolutely beautiful, and you can create trees, you can create shorelines, you can create absolutely beautiful things with Monte Carlo methods. So this is just a picture I found online. If you Google on Google Image Monte Carlo methods, you can just see some absolutely gorgeous stuff, and I highly recommend it because it's very fun. And anyway, so this is some smoke-like thing that's probably made using a very simple algorithm and some very complex imaging software. All right, so I guess we're going to start. Let me just move this here. So what are Monte Carlo methods? What is this thing we're talking about? There's a lot of catchphrase in the literature and in the news, and a lot of confusion as to what exactly this stuff is. What people use Monte Carlo methods for is incorporating probability into analysis. And what I mean by probability is a sequence of it occurs when we have a sequence of measurements, and these measurements they don't have a consistent reading. An example of that would be temperature. Temperatures fluctuate. If you don't have a consistent reading, but you know that you're measuring the same thing, it's usually a use when you're trying to incorporate probability. For those of you who want a much more rigorous definition, and there really is a lot of very good IT literature on it, I highly suggest that you Google on Wikipedia random processes, find a really good definition as to how exactly probability works in the real world. But for now, by the way, I'm not a mathematician, so if that definition isn't rigorous enough for you, that's I'm perfectly comfortable with that, and we won't segue into that. We want to use it when we want to know if a set of scenarios can happen, but we're not sure if they will happen. And that's really, in a nutshell, what Monte Carlo methods are about. We know we have these scenarios out there, and we know that they could happen, but we're not sure if they will happen. And what Monte Carlo scenario methods work is that we, based on some rule, we pick these different scenarios, and eventually we expect to get some result out of it. How they essentially work is that we try to structure the world, or what we're trying to analyze, as a system. And what we'll do is we'll format the world in many, many little steps. Step 1, step 2, step 3, up to step infinity, or as many steps as we want to take. And then each step or iteration will involve some realization of our world, or some state that our system is in. Eventually, what we expect is that the system will converge to a desirable measure, or something that we're actually looking for, something that we can usefully analyze. And this is sort of a picture of what we're talking about, is that our measure, or what we're interested in, it fluctuates over time, but what we expect is that as each step, or each iteration, realization of the world, eventually it will converge to some useful measure that we can analyze. Are there any questions about that?
Anyone that's new, just type away in the text chat box. Everyone's getting muted as new people come in. I'm on. Any questions?
Another way of calling this is integration, or mathematically integrating, and it's very similar, but I prefer to think of it this way, simply because it's a bit more intuitive insofar as the way we interact with the world is we measure things, and eventually we hope that our measurements will yield a consistent result. While integration is more of a mathematical concept that's it's a bit less intuitive, or at least I find it less intuitive.
We got a question from Syed. I would say Syed.
Why do we need to converge to a desirable measure from Syed? Well, why do we need it to converge? Because if it doesn't converge, then nothing. And that's actually not an unreasonable question. If we can create Monte Carlo systems that don't converge, but the problem is if these systems don't converge, then we don't get anything useful out of it. You could think of it as if you could imagine our world today. We have the laws of physics that binds us to the ground, that makes sure that mass has certain properties, that light goes at a certain speed, and so forth. But if the system doesn't converge, or if the rules of physics don't apply, and let's just say they don't tend towards anything, then you're just getting sheer randomness. And in that case, there's just nothing useful from that result, or from that system. It's not really a system in a sense if it doesn't converge.
Two more questions just popped up for you.
By a measure, do you mean a sense of probability measure? Absolutely not. I'm not a mathematician. Probability measure is something that I'm not comfortable speaking about. But when I think of measure, when I use the term, I mean it in the sense that it's just something that we can observe, or something that we can see. You could think of it as light in front of you, weight, whatever system you're trying to record over time. And do I mean converge to a value? Yes, I mean to converge to a value. But it won't necessarily converge to a value. You can have Monte Carlo systems that will converge to a function, or will converge to a set of relationships. So it's not necessarily true that it will converge to one value necessarily, but you would expect it to converge to some stable process, or some stable outcome, whatever that would be. So it's really about creating stability rather than the value itself.
Just somebody asked about what is converging.
But these are very good questions, and to be honest, I'm not as competent as I would like to be in answering them. These are really questions that you would ask someone with a PhD in mathematics to answer, because they're much more trained in these sorts of very fundamental questions. And I'm more of a technical person in the sense that I'm dealing with the applications of these things to the real world in business contexts and so forth. All right. Here's a nice overview of various Monte Carlo methods. What we're really trying to do with this is trying to do something with reality. So the way I've described it is we have reality, which is in this lovely little cloud here, And from reality, we're trying to create a model, or we're trying to create an idealized version of that reality, which obviously is simplified, because otherwise it wouldn't be a model. But on the other hand, it still has some properties that we think relate to reality. Well, what each Monte Carlo model will have is it will have inputs. So we'll have something that, some bits of information that we have from reality that will be the starting points of the model. The model will also have a system, or a way that the inputs are taken and they react with each other to create something. That's really the heart of your model, or the heart of what's happening. What a Monte Carlo model does is it takes the inputs and it integrates it through the system. Then we will get outputs as a result of taking the inputs and running them through the system. What happens in the end, and any person who has ever worked with Monte Carlo models will tell you, is that once you've used the outputs, that is, once you've taken the inputs, run them through the system, and gotten outputs, you will always take those outputs and feed them back into your inputs to change your inputs. That is, in order to validate your outputs, you'll have to have some measure to compare them to your inputs. That is, if you look at your outputs and you see, okay, are they valid? Are they reasonable? If they are, then you're fairly certain about the quality of your inputs. However, if they give you weird results, you may actually consider changing the inputs of your model to make sure that it works. But this is what everyone does, and you have to do within any Monte Carlo system. A more sophisticated analysis is to take the outputs and actually change the system itself. That is, look at the results of your model and change how the inputs interact with each other depending on those results. However, this is a much more sophisticated level of analysis, and it's usually only left for people who are much more technically able to deal with these models. Generally speaking, in risk management systems, in physics laboratories, it's only the more senior researchers or the people who actually created it rather than the junior level people will actually use this sort of analysis of taking the outputs of a model and actually changing the system. Generally speaking, junior people will be involved much more with measuring outputs and changing the inputs depending on what outputs come out as. This stage is the stage that I will label as the synthesis component of the Monte Carlo model. That is, what we're doing is we're taking reality and we're drawing from it an entire system. That is, we're synthesizing it, and we're trying to create a complete system that's self-reinforcing. That is, it's complete, and we think it's congruent with what we see in reality. After this, however, there's another stage, that is taking what we have from the model and inferring about reality. And I really want to emphasize at this point that this inference stage, or looking at the model and inferring about reality, is a wholly separate form of analysis than this stage, which is taking reality and synthesizing a model. Unfortunately, especially in a lot of quantitative finance literature, you'll have very, very strong synthesis of reality to the model, but then very, very weak linkage between the model to reality. That is, you'll create these very, very long, very, very sophisticated equations and relationships in these Monte Carlo systems, but then there'll be very little effort to actually say, okay, well, this is how this model actually works. This is how this model compares to real observed market prices. This is how this model compares to real values of whatever we will see. And it's really important for you as a decision maker when, I'm sorry, Brian, could you get that to stop, please?
Yeah.
It's really,
Sorry.
really annoying.
Sorry, man.
All right, thank you. It's really a separate stage to infer from your Monte Carlo model than it is to synthesize your Monte Carlo model. And in some organizations, they'll actually separate entirely those two components. So you'll have the model validation component of a bank, and you'll have the developers, or the people who are creating these models. And it's really important to be especially wary of this stage here, that is, looking at the model and inferring from reality, because this is a very delicate stage, and it's almost 100% guaranteed that this is a stage where most models go wrong. That is, people will take the wrong inferences from the models, or they'll think that the model tells them things which in fact it doesn't. That's why I often get very frustrated when I hear, especially in the media, when they talk about this component, which is, oh, well, this model doesn't work because it did X and Y and Z assumption when it was synthesizing from reality. But in fact, it's not the fault of the model or the fault of the creator of the model. They may be simplifying assumptions. These simplifying assumptions often are necessary to make the model tractable or actually implementable. It's really when you're taking the model and you're inferring from it onto reality that you have to be very careful. Are there any questions about that?
Yeah, one just popped up. Sorry.
So is it possible to over-optimize and make too specific so it doesn't apply to reality? I believe, Sandra, what you're referring to is model overfitting, and that is definitely an issue with research and finance models in general. However, that is not specific to Monte Carlo methods and Monte Carlo models. Monte Carlo models and Monte Carlo methods actually have very have pretty much very little relationship with optimization as such. And in fact, when you're optimizing, you actually have to optimize without using Monte Carlo methods. That is, what you'll do in practice is you'll simulate from a distribution, and then you'll optimize over those realizations, and then you'll simulate from that some more. So it's really it's related, but it's a separate form of analysis, optimization, than it is from Monte Carlo methods, which are really creation of alternatives, if you will.
Two more questions just popped up.
Yes, function mining. Yeah, absolutely. The topic of overfitting and function mining, it's very interesting, but it's not related to Monte Carlo models and Monte Carlo methods. In fact, they're wholly separate topics, and I'd like us to avoid mentioning it. Though it's an interesting topic for further discussion. We'll definitely look into maybe doing a presentation on that at some point. The Monte Carlo models, they come in a few various flavors. I've given up 4 here just to give you guys an idea of how they work on a more sort of simple basis. And really, they all have very simple building blocks, and how those building blocks come together can be extremely complex. This is really a simple Monte Carlo model here, where you have this initial start state of n, and then you have 3 different options. You have option A, option B, and option C. And these blue arrows are some probability space over which option n can be state n. I apologize, it should be more specific. State n can be state A, B, or C. One step further is to take a two-stage Monte Carlo model. That is to say, well, okay, instead of having one stage that is stopping at A, B, or C, we could have that each A, B, or C in turn has another stage where it goes, in this case, to D and E, or that each realization splits into another 2 realizations. I call this a two-stage Monte Carlo model, but you could have an n-stage Monte Carlo model or an infinite-stage Monte Carlo model, where each realization in turn splits 2 other alternatives. These are often the simplest models and the easiest to understand from a user's perspective if someone's trying to sell it to you. A more sophisticated approach is called mixture modeling. That is, instead of playing around with the states. So in the simple Monte Carlo model, we had 3 different states, and the 2-stage extension of that was to allow more states as a result of the previous states. In mixture modeling, what you're doing is you're saying the probabilities themselves, or the transition between various states, itself has a distribution. That is, your chance of moving from state A to state B itself has a distribution of states. And this is a much more sophisticated...
Yeah, I'm on it.
This is a...
Hello, Dan. If you could mute yourself. Okay, done. We're full house.
All right. This is a more sophisticated approach, but it's still very simple in that if you could remember back to the previous slide, let me just go back here. the inputs directly translate into the system, which directly translate into outputs, and the transition is linear. That's the nice thing about these three models here, is that the effects, and you can, for those of you who are experienced with this, you'll understand what I'm talking about, is that when you're constructing these models, the impacts are very linear from a perspective of an input to a system to an output. And it's very easy to manage these models. Even mixture modeling, while the result may be a bit less intuitive, they're still very stable and very easy to, and tractable, really. The most sophisticated approach is our Markov chains. And in Markov chains, what you have is you could imagine a sum product, for those of you who are more into math, is that each realization of the state builds on every single previous realization of the state. And in this case, what you have here is that A not only directly impacts B, but it also impacts C and D. That is, if we're in state D right here, what happened in C, D, and A directly impacts us, and this builds up over time. Markov chain systems, random walks are an example of a Markov chain, are very, very sophisticated systems, and they're very nonlinear. And if you could remember back to what I was referring to, where they don't converge, a lack of convergence for the measure, Markov chains are often where those pitfalls happen. That is, there's nothing that prevents. Let me rephrase that. Markov chains can give you very, very unrealistic results very, very easily, and they're very, very sophisticated. And I highly recommend for those of you that are interacting with Monte Carlo models, if you're not very familiar with how to work Markov chains, if someone brings it to you, run away, to be honest, because this is something that you don't want to deal with. It's as if a car dealer came to you and said, hey, listen, I got this great car, it's a Ferrari and it costs $1 million, and it's great for getting your milk. Well, I've never had a Ferrari, but for any of you who have ever seen one, you can probably imagine that it's not great for getting milk, because the suspension's not particularly comfortable. There's not a lot of trunk space. I wouldn't recommend it. So from that perspective, I think you should think of Markov chains in that same way, is that unless you really, really understand what's going on, try to avoid models with Markov chains. By the way, this caveat is for people who are looking at things that they haven't constructed themselves. From a developer's perspective, if you're really trying to get a feel for Monte Carlo methods, Markov chains are really a good pillar from which you can establish your knowledge. That is, if you feel comfortable with Markov chains, chances are that you can chances are that you can feel comfortable with other methods as well. Are there any questions about this?
Anybody, just chat in the chat box. I guess not.
All right, good. That's I'm actually glad, because it took me quite a while to create this.
So far, so good.
Yeah. All right, a natural question to transition from this is, okay, well, what are Monte Carlo methods actually good for? All right, great, Alon, you told me about these things. Well, what can I use them for? How are they actually useful in real life? And one thing that they're really good for is examining complex aggregations from simple actions. And what do I mean by that? There are a lot of things in our world that are complex aggregations. That is, if you could imagine the human body is really a very complex aggregation of an infinite number of tiny little processes that are happening within us. You have, at the DNA level, you have DNA and RNA, and by the way, I'm not in biology, but you have these different levels of processes that are happening that comprise the human body. So from that perspective, the human body is a very complex aggregation. However, we know that the actions from a human body, and for those of you who are involved with cancer research, I actually happen to be involved with that at an earlier point in my life, they're very, very complex actions. However, there are other complex aggregations that actually result from simple actions. An example of this would be a horse race, for instance. It's pretty easy to measure exactly how fast the horses are going and see the end result of which horse wins. What our Monte Carlo methods are also good for is incorporating uncertainty into our analysis. That is, when we're doing analysis and we want to be conservative, that is, we're a bit unsure as to our confidence with respect to any given result, we can actually very easily incorporate Monte Carlo methods to make our results a bit more conservative. Another nice application of Monte Carlo methods is to explore unintuitive results. That is, us as human beings, and for those of you who are very into chess, I'm personally not, but I have a friend who's very intensively involved with chess, and he'll tell me that for those who really play chess, playing computers is one of the most frustrating things ever, because computers, they explore the entire potential space of possible actions that a chess player could make. And they often will use moves that, for a human person who's playing chess, would think are stupid, or they think they won't work. But the computer, because it's already seen everything, or because of its stupidity or its brilliance, depending on your perspective, it will use these results regardless. And often that means is that it's very hard for a human to, or in this case of chess, a human can't beat a computer simply because the computer has already foreseen the potential moves that a human can make. And that's what's a really good example of how computers can help humans in understanding the world, is that Monte Carlo methods can give us very unintuitive results that we'll actually have to tackle with. Another application of Monte Carlo methods is really to simplify a complex system. That is, to take something that has a lot of parameters, a lot of features, a lot of stuff, and really simplify it to one or two or three key components that we're really interested in. However, Monte Carlo methods, they also have some disadvantages. And by the way, I'll be exploring in a bit more detail about these key points. What are Monte Carlo methods really bad for? And an example of this is examining simple actions from complex aggregations. And an example, what I mean by this is, let's say that we have a complex result. A very good example of this, going back to the human body, is a person is sick. A person is sick, okay, well, we have this aggregation which says a person is sick. However, to examine the simple actions, that is to infer why that person is sick, we have all these different potential causes, and they can often interact with each other, and it's almost an intractable thing from a pure, from, how would I put this? Imagining that if you knew nothing about medicine, that is, if you had no biological background, and you're just trying to see what reason the person would be sick, statistically, you would have a very, very difficult time. And this is what I mean by examining simple actions from complex aggregations. That is, the result of a complex aggregation has so many actions that could lead to it that it's just very hard for you to infer exactly how that happened. Oh, sorry about that. Another thing that Monte Carlo methods are really bad for is getting a realistic result. There's nothing in Monte Carlo analysis that provides you with any guidance as to what is a reasonable result or a good result. Monte Carlo methods, they just give you results. And anyone who's dealt with this will know this is a huge pitfall of Monte Carlo methods. And it's often a problem when communicating with people who aren't familiar with them or from a non-quantitative background, in that they think that these methods can give them something more credible, something more reasonable. But they have to understand, and it's very important for you out there to understand, that getting a realistic result is not what they do, and it's not what they're designed to do, and they're not good at doing that kind of thing. Another issue with Monte Carlo methods is really communication, and this is something that we struggle with at the consultancy, and I personally struggle with in my daily life, in trying to communicate to people exactly how these methods work and what they're useful for. And that's something that we're definitely trying to improve with these videos, and Brian's working on this as well. And it's definitely getting better, but it's still absolutely a problem, especially for those who don't have a very strong background in mathematical analysis. They often have a very difficult time understanding probabilistic thinking, which is really essential to understanding Monte Carlo methods. Another problem with Monte Carlo methods is robustness, in that Monte Carlo methods are very, very sensitive to the inputs that you put into them. If you change one thing even slightly, you can often get a totally different result from an end perspective. And that means that you have to be very, very careful with how you approach doing it. It really is not a robust system. It's not like a cell phone that you can just drop it on the floor and pick it up and it will work the way it does. Monte Carlo methods are really a very, very delicate thing. Another thing is speed. Sorry, go ahead.
Sorry, I'll let you make this point, but someone just asked a question from Jason.
Can't make a realistic result. Can you expand on this? Yeah, absolutely. When people refer to realistic, let's go back for a second. Let me just finish the speed point, and then I'll address your question. Another issue, which used to be much more of a problem in the past, though it's actually funny, because as computers are getting faster, we're finding more and more enhancements to Monte Carlo methods that create incredible demand for computer power. So from that perspective, it's almost limitless in demand for computing power. But especially in the past, speed used to be a very big issue with Monte Carlo methods. So now that's becoming much, much less of an issue, and there's still a lag that exists, especially for the more comprehensive analyses between pushing a button and actually getting a usable result. When you're referring to making a realistic result, realism is something that we as people understand and we use in our daily lives. That is this thing reasonable considering what we know about the world? Monte Carlo methods, they don't address that at all, and it's often a reason why people accuse computers of doing things that really computers aren't meant to do. Computers, they can't. And when I'm referring to computers, I think Monte Carlo methods are very computational in the sense that they just give you a result. They don't actually have any feedback mechanism that will make sure that your result is more reasonable than any other result. And it really just gives you what you're looking for. For those of you who are programming or with the programming, will absolutely know that any code that you write that doesn't work is the coder's fault. It is never the computer's fault. It's always the coder's fault, and you'll find out somewhere. It just takes a matter of time to figure out exactly what the coder did wrong. But you can never actually blame a computer for this. And when I'm talking about getting a realistic result, I mean, the Monte Carlo method is the exact same way. You can't blame it for not giving you a realistic result. It's just not capable of thinking and working in those terms. And I think it's very important to be aware of that when you're dealing with these methods. You don't. Yes, Andrew. That's a very, very topical point, and it's very true. Computers almost always fail on that task. And for those of you who want to have some fun, you can go. There are these chat sessions that you can have with these AI programs, and it's absolutely hilarious. The results they'll give you.
I think Andrew's going to have another comeback. It's just one limitation. Go ahead. Oh, Siri. Yeah. Okay.
And the Siri.
Just waiting on him. Are you referring to Talk 30 to me to Siri? Yeah, exactly. Similar. Yeah, similar.
Yeah. I'm sure Apple's put something very PG in there. But,
I could try it out right now on the iPad if you want. Here we go.
I think it's best that we leave this for later and we'll put this on the presentation. Sorry.
Of course,
I don't want any false police coming after me.
All right.
Now we're going to get a bit more into complex aggregations and what I'm really referring to when I'm talking about that and how it works with Monte Carlo methods. In reference to what are these things good for? Monte Carlo methods, they're really useful for problems where we can easily measure the complete set of actions within the system, but we're really not sure about how those actions aggregate in the end. Examples of this include insurance, which is actually dear to my heart because I've worked in the industry and applying Monte Carlo methods for insurance. Sports are another absolutely excellent example. I've seen really, really good Monte Carlo analysis on different different sporting strategies. And another example is demographics. What these three things have in common is they have very, very simple actions. There may be many of them, but they're very easy to observe, and they're very easy to model in the sense that there's a limited number of correlations, and it's really the space of possible scenarios is limited, and that's really where Monte Carlo methods shine. More sophisticated examples of this include operations research, where Monte Carlo methods are actually extensively used. For example, if you're a manager at a very large company with many manufacturing facilities and you want to see the optimal mix of production, often they'll use in very sophisticated Monte Carlo analysis to find the exact rate at which you should produce or open and close factories. However, there are other reasons why Monte Carlos may be bad. For this example, simple example of complex aggregations. In complex problems where we don't know the complete set of actions, and we have to infer from the aggregate outcome. And for these things, Monte Carlo methods are really, really bad, and I highly recommend that you do not use them for this as such. Examples of this include market prices, and when I say market prices, I mean all market prices. Scott Summer, who is a very big blog, well-known blogger on monetary theory, says you can never infer from a price change or a reason from a price change, and it really is true for Monte Carlo models. If anyone is trying to sell you a Monte Carlo model that promises you that they're going to make money out of it based on market prices is wrong. They're just absolutely wrong, and there's no way you can make money with this. For those of you who are a bit confused as to why banks use Monte Carlo models, they use Monte Carlo models for two reasons. One, regulatory purposes, and two, bridging the gap between market prices and their balance sheet. In that banks, they hold securities and complex instruments and complex exposures on their balance sheets for long periods of time without ever getting feedback from the market as to what the value of these things are. Because for accounting reasons and internal management reasons and just corporate functions, they need to value these things. They use Monte Carlo models, but those models are not, in any sense of the term, credible. They're really just there for governance purposes. A believer in efficient markets, I guess. How should I put it, Jason? You don't have to be a believer in efficient markets to believe that market prices are better than Monte Carlo models. And anyone who has worked with Monte Carlo models will admit that market prices are just a better guide. I've yet to see any researcher claim that Monte Carlo models give you better prices than markets. Because for the simple reason that in markets, you're betting your money. In Monte Carlo models, it's whatever you want it to be. So, you know, if you can imagine if you're sitting with your favorite uncle who always comes to the dining room table on Thanksgiving and always parrots for whatever party or politician that he likes, you know, he can say this, of course, because, you know, he doesn't have money on the line. But if you tell him, you know, let's just say he's Uncle John, if you tell him, Uncle John, you know, what about, you know, we have this system like this, it's called in trade, and you can bet your money, and you can actually, you know, prove to the world that you're right and be rich out of it. And often John will, you know, he'll be a bit sheepish about it because he knows that, you know, he's just talking. He doesn't really know what he's talking about. And market prices are very much the same thing, where if you're going to bet against a market, don't use Monte Carlo models. That's really not what they're for. Another example of this is biological systems. And it's actually very interesting in that for microbiology, that is modeling how proteins fold and DNA and RNA and so forth interact, there's actually a lot of very interesting advancements in Monte Carlo methods for using these to understand exactly how these very microbiological processes work. But for very large biological systems such as the human body, ecosystems, a forest, something like that, you just can't use, Monte Carlo methods do not give you a credible result. You may see them in academic papers, and often what the academic papers are trying to do is say, if the world looks this way, this is what you would get. And that's really the kind of analysis they're doing with Monte Carlo methods. But they're really not trying to learn something about the system or be able to predict something about the system from this kind of analysis. Another example of this, and this is near and dear to my heart because I'm not a fan of Canadian weather, is the weather, really, because they'll actually, and this is one thing that really upsets me, is that climate change scientists, and by the way, I don't mean either way in climate change, but what I do know is that using Monte Carlo models, and this is what a lot of the panelists in the UN use, using Monte Carlo models to prove that climate change is happening is just absolute nonsense. They cannot do that. There's no way that they can model a complex system as the Earth's atmosphere using Monte Carlo methods. That is false. I don't care what anyone tells you. This is not on a scientific basis. This is just a fact. And I highly suggest that if anyone comes to you and says, listen, I have this Monte Carlo model that will show you the world, be very wary of it. Are there any questions about this?
Anyone got questions? Type them up in the chat. Guess not.
All right, we'll move on then. Another sort of segue in Monte Carlo methods is trying to approximate reality. That is, trying to get a hold of what it is that we see around us. And an example of a good use of Monte Carlo methods when we're trying to approximate reality is using what-if scenarios. That is, when we know that the current realization is not the only possible scenario that happens. That is, if I wake up in the morning and I decide to have cereal for breakfast, I know that I may not always have cereal for breakfast. I could have oatmeal, I could have some scrambled eggs, I could have some bacon. There could be multiple different things. And Monte Carlo methods are really good for when we know that what we observe right now isn't the only actual result. There could be other results out there, and that's where they really, really shine. Another good use of Monte Carlo methods is penalizing overconfidence in a measured result, and this is a very big issue, especially in business, but not just exclusively in business. You see this in all spheres, where people generally have a overconfidence in their analysis, that is, or their personal experience. They believe that the observations that they see in their daily life is indicative of the world at large. And often, us as people who are more quantitative, it's our duty to make sure that these people don't run amok with their assumptions. And it's really important to understand that Monte Carlo methods can penalize you for being very, very confident that the result that you have may not actually be the most likely result or the result that you're looking for. And they're really useful for that. So if someone comes to you and says, I have this Monte Carlo method, and this can test how good of an answer the answer that we have is, that's a really good application of that kind of analysis. Here's a bad use of, or what I think is bad practice when using Monte Carlo methods. As I mentioned earlier, it's finding reasonable scenarios. That is, if someone comes to you and says, I want to find the most plausible scenario for who's going to win the Super Bowl, or who's going to be elected next president. Monte Carlo methods, they can't answer those kinds of things, and it's not the kind of analysis that you want to use. Another bad use of Monte Carlo methods is measuring the likelihood of various scenarios. Monte Carlo methods, they take the likelihood as an input into the system. At some level, even if the likelihood is somewhat determined within the model, there's going to be some input that's going to determine how likely each one of those scenarios are. And from that perspective, Monte Carlo models, they do not tell you how likely each scenario is. They can only say, given certain assumptions, this is what you can see. And it's really important to understand that when you're working with such models, is that the distribution that you see in front of you is not the only distribution. It's the distribution based on the assumptions and the system that you've created. Now we're going to have a little digression here, or a side note that actually relates to Monte Carlo methods, and that's type 1 and type 2 errors. And this is actually very interesting. I was just thinking about this. I don't know about yourself, but I learned about type 1 and type 2 errors in university, and I didn't understand it for the life of me, to tell you the truth. It made no sense. I just followed the practice questions, and I passed the quiz. And Wikipedia, which, by the way, is supposed to be an authority on good practice as far as simplifying and explaining things, this is the table that they provide to help you understand what type 1 and type 2 errors are. Now, I don't know about yourself, but for me, I have absolutely no idea what a null hypothesis is. I'm not sure what this H0 is. I'm not really sure what true is. You have this false positive, false negative, true negative, true positive. You have these correct outcomes, so it's a correct true outcome. I mean, these are even Wikipedia has difficulty with communicating with this, and it took me a while to gather together some resources to sort of think about this and relate it to Monte Carlo models. But it has a really interesting corollary with what I'm talking about above. And this is the table that I came up with of how to think about type 1 and type 2 errors. That is, we have sort of two categories here. We have what our null hypothesis is. That is, what is our knowledge of the current scenario? So it could be our knowledge is I'm alive, the building is 10 feet high, my hair is black, and so forth. So that's some knowledge. So that knowledge is your null hypothesis, or you can think of it as your prior for those of you who are Bayesian. And we have sort of the judgment that we make about that knowledge. Null hypothesis is a Dickey-Fuller.
Yeah, just so you know, it's like a Dickey-Fuller test. We're just testing a time series if it's.
Oh no, absolutely. That's a more application. I think on a more sort of broad level of what is this that we're trying to deal with here.
I apologize.
And that's absolutely a good example. Is we have sort of two components. We have our null hypothesis, or our knowledge, that is, or our prior, or something that we think we know. And then we have our judgment about our null hypothesis, or our judgment about that knowledge. And what we can do with that knowledge is we can accept it, or we can reject it. And that knowledge can actually be true, or it can be false. And this is actually a fairly reasonable way of thinking about the world, is that, you know, there's the real world, which, you know, some things are true and some things are false. And then there's sort of our judgment about the world as to whether we accept that these things are true or we reject that these things are true. And type 1 errors occur when we accept, then we reject what is real knowledge. That is, if I go and I see an orange and it actually costs $1, and my knowledge about that orange is that it costs $3. That is, I reject it, $1, that's a ridiculous price, nobody would ever pay for that. That can't be true. A type 2 error is the converse of that. That is, when we accept knowledge that is in fact false. That is, when we go around and an example of this, what I think would be, though I'm sure some people out there will disagree with me, is witches, for instance, or leprechauns, or unicorns, or any of those other mythical creatures. That is, we're accepting knowledge which is false. I mean, I'm sure I'll be upsetting some of you, but these creatures do not exist, or at least I've yet to see convincing evidence that they exist. And this is a judgment. This occurs when we're accepting something as being true, when in fact it doesn't exist in the real world. And how this relates to Monte Carlo methods, which is a real funny, Andrew, funny. And how this relates to Monte Carlo methods is that Monte Carlo methods are really good at us understanding type 2 errors. That is, us avoiding accepting knowledge which is in fact false. For those of you who are familiar with business situations, you'll understand that most business decision makers, for reasons that I'm not 100% sure of, they're much more worried about type 1 errors than type 2 errors. That is, they're much more worried about they're much more worried about missing out on that big deal or not appearing knowledgeable when something happens than they are about type 2 errors. That is, thinking that they know something that when in fact they don't. And Monte Carlo methods are a really good way of rooting out knowledge that we think we know when in fact we really don't know it. Are there any questions about it?
I don't think so. I don't know if you read Mark's comment.
Nitpick accepts is not equal to not reject. You're right. You're right, Mark. But you know, how do I put it? This is how I understand it, and it makes it easy for me. And I'm really trying to simplify to make it easier for other people. There are more rigorous ways. There are definitions. We can spend hours breaking this apart. But for me personally, I found this very informative, and I hope that those of us who are for those of us who aren't as skilled in this kind of thing, this can help them at least get a flavor for what's going on when we're talking about type 1 and type 2 errors. People, as I mentioned earlier, people are very sensitive to type 1 errors, or they just don't want to appear as though they're losing over a trend or missing out on something. And as I mentioned, Monte Carlo methods are really a good way to help us account for type 2 errors. There are actually other applications, other uses of Monte Carlo methods, which I'd like to mention. One is just expanding the possible opportunity set. And what it does is Monte Carlo methods, they provide us with a range that's hard for the human mind to replicate. That is, I don't know about other people out there, but personally I'm very, very bad at creating random numbers and thinking in terms of more than 7 or 8 dimensions. It's just very hard for me personally to handle these things, looking them on a bit-by-bit basis. And Monte Carlo methods are a really good way to, unconstrain yourself from those limitations and really just infinitely expand how many possible arrangements you can come up with. However, the problem with these scenarios is that they're very hard to justify and or communicate, and this is especially true for those without a quantitative mindset. That is, when you go to a decision maker and you tell them, here's 13 or 14 or 15 different parameters, and this is one realization of it, that person is going to look at it and say, well, that's ridiculous, that would never happen. And it's hard to, I found that it's hard to approach them and tell them that it's not so much that you have to weight each scenario by its likelihood, that it's not enough just to look at each scenario in isolation and accept or reject it based on its plausibility, because the distribution of scenarios or how they work in conjunction actually has very important information. However, just be aware that this is a big communication issue with Monte Carlo methods. Another useful application is sensitivity testing. That is, it's very easy for us to incorporate conditional changes to a system. That is, keeping a system fixed and changing one input or changing one component of the system and seeing how that changes your end result. This is a really nice application, especially for those of us that may not necessarily be confident in the robustness of the system. However, this doesn't address the disadvantages of using conditional analysis. That is, conditional analysis is very, very, it's hard to extrapolate, to be honest, in the sense that if you have, using conditional analysis and changing one parameter out of, let's say, 5, you don't actually know the correlations between those 5 parameters, and you don't know the particular combinations of those parameters that are more plausible than others within the setting of a Monte Carlo model. And it's very important to understand that while Monte Carlo methods can help you understand the conditional changes to a system, they still don't address the problem of conditional analysis. Another nice application of Monte Carlo models is really reducing complexity. That is, allowing us to comprehensively measure and monitor a system in a way that we really just couldn't do in real life. That is, if I wanted to real-time track every single individual within the city of Toronto insofar as their location, it would be incredibly data-intensive and very, very expensive to do. However, if I could create a Monte Carlo model and just make sure that certain inputs are tracked to the real inputs real time, it's actually much easier for me to sort of condense that very complicated information space into something that's more tractable and easier to manage. However, it's important to understand that this is only as credible as the model that is being simulated. That is, when you're reducing this complexity, sometimes you can actually distill or remove important details that will make your model not reflective of reality. And it's really important to understand that these models, they're just models. They're not reality, and they're only as good as the people who make them. So what are the key lessons for some decision makers from these models? And the first is just don't trust Monte Carlo methods blindly. If you have this Monte Carlo models, and I just put this from a previous slide to keep you inspired. The key questions that you have to ask before incorporating this analysis are, will the Monte Carlo methods contribute to the analysis? And this is a very big point. I especially see this in a lot of business settings where you'll have a quant that's very enthusiastic and very excited, and they'll say, let's Monte Carlo it, when it may not actually be answering the problem that the analysis is supposed to face. And it's really important to understand that question before you decide to make the next step and actually create or use such a system. Another question that you have to ask, and this is an absolute must, is the architect of the model capable of managing this? And I've seen this time and time again where these models and systems are created by people who end up leaving or retiring or doing whatever it is that they do, and other people will take in charge, and they will not understand these systems and not be able to manage them. And from your perspective, if someone's selling you something, you have to ask yourself, can I manage this? Do I understand, and am I capable of being responsible for this before you decide to embark on it? Because these things are very, very time-consuming. If someone comes to you with a model, another reasonable question is, are the assumptions of the model reasonable? That is, if someone comes to you and is trying to sell you something, that's really your first question that you should ask yourself. What are the assumptions that this person has, and are they reasonable? Because that's something that is very easy for someone who's not quantitative or does not know all the details to ask that person, and they should get a clear, reasonable answer. Another is, are the outputs of these models realistic? That is, this should really work in conjunction with the assumptions. That is, are the assumptions reasonable, and are the outputs reasonable? What I think people should really avoid, and this happens constantly, especially with those with, it's funny, I prefer to categorize a woman into two people, those that are very good with quantitative methods and those that can understand them, but they're not necessarily skilled in that dimension. The worst kinds of people are people that border the middle, that is, they know enough to be obnoxious, but they don't know enough to actually contribute. And this is very important within the context of this table here, where what these people will do is they'll look at the outputs and they'll actually try to drive the system. That is, instead of questioning the assumptions of the model and looking at the realistic of the outputs, they'll actually try to drive the system to what they think is reasonable. That is, they'll say, well, this component of your system is unreasonable, or you should try changing these parameters to get this desired result. And that's actually not the way Monte Carlo methods are supposed to work. You're really not supposed to drive the system to get results that you want. You really should take reality, create a model, and then take from the model and validate reality. If you're using reality to drive the model, then you're probably doing something wrong. And it's very important to understand that. The final question that you should really ask is the model properly validated? And this is probably the most important component when using the models. That is there some external benchmark that you can use to make sure that the model's results are reasonable? Because otherwise you really have no idea of how close your model is to achieving the results you want. And that's really an important part. That is, you cannot trust these models regardless of what they give you. You always have to have some external validation. Are there any questions?
Anybody want to ask in the chat? Anybody else? Yeah. Oh, here's one.
Yeah, absolutely. For conditional analysis, when I'm referring to conditional analysis, that is, if you have let's say a model and it has more than one parameter, conditional analysis is changing one parameter values while keeping all the other parameters fixed. And we often do this to answer questions that relate to, well, okay, well, if I change this parameter slightly, what result will I get? And the problem with conditional analysis is that not everything else is equal. That is, in reality, all the parameters are changing all the time together. And when you use conditional analysis, you're implicitly assuming that everything stays the same, when in reality we know that it's just not true. And it's very important to understand that when you're using Monte Carlo models and you're conditionally changing things, that you're running the same pitfalls of using an Excel spreadsheet or any other method that you will when you're conditionally changing things. That is everything. Not everything else is equal. Some things will change, and it's important to understand that when you're modeling something. Did that answer your question?
Should. Any other questions at all? Yeah, must have. One from Steve.
How do you define robustness? That's a good question, Steve. Robust. When I try to think about robustness within at least a business context, I try to think of something that I can give to multiple people and change it slightly, and I'll get reasonably similar results. I think a better example of this is in the physical world. That is, a car is reasonably robust in the sense that it's a car. It sits there. You put in gas. You drive it. If it breaks, it breaks. But otherwise, it's not that amorphous. It's not as if the car will turn into a swan at the flip of a hat. Unfortunately, Monte Carlo models are literally like that, in that they live in a world where cars turn into swans, and swans turn into bacteria, and then bacteria turn into poems. And it's really important to understand that these models are just very sensitive, and they're not robust. They're not something that you can drop on the ground and kick around and expect it to work the way it did. You can change, and anyone who's experienced with building these things will tell you, is that slightly changing even one little thing can often lead to very nonlinear solutions.
Andrew's got a question.
Yeah, there's a statistical definition for robustness. There's a philosophical definition for robustness. There's a mathematical definition for robustness. There's a lot of definitions for robustness, and I highly recommend that you look at all the different definitions. I'm not going to dwell for this presentation on definitions because it's a very murky road, and I'm not qualified to talk about it. But I highly recommend that you have a qualitative understanding of what robustness is. For example, mean versus median.
Do you want me to bring him in online? Get him verbally in?
Yeah, I think that might be easier for everyone involved.
Okay, hang on, Andrew. I'm going to get you unmuted. Andrew? Andrew? There you go.
Can you hear me?
Yep, we can hear you. Go ahead.
Okay, yeah. What I was thinking of is that the example I heard for robustness in statistics was if you say compare the mean and the median as a measure of central tendency, the median is a lot more robust because if you were to add or remove observations in the tail, then the median will be affected much less than the mean. So if you consider, say, a mean of 50 and observations are all between 45 and 55, and let's say you have 50 observations, you then add on one observation of 10 million, the mean will change by a huge amount, whereas the median will be virtually unaffected.
You're absolutely right from that perspective. I want to emphasize with that particular example that you use that it depends on what you're looking for as far as robustness. If you're looking for a volume or a total measure, that is, if the distance between the points is very important to you, then using a median is not actually useful because a median is just the absolute distance or a ranking between the different points. And just on a more subtle point, you're absolutely right that if you're concerned mostly about outliers, that is, adding and removing observations will change your key statistic, or in this case a median, then a median is absolutely more robust. However, if you're concerned about the total distance, that is, the difference between each point in your group, then a mean is actually much more robust from that perspective because it makes sure that no matter how you arrange the dots, you'll still be able to collect all that space or all the difference in space. And so it was probably my fault that I didn't elaborate on this because it's a very complicated subject. But you raised a good point, Andrew, is that for any of the keywords that I use here, I highly recommend that if you don't understand, if you're a bit uncertain, or if I didn't clarify, just dive a bit deeper and look into it to help yourself understand. Because ultimately, I can help you just as a starting point, but it's really up to you to sort of have that sort of gut feel that I'm sure Andrew has as to what these words mean.
Another context in finance in which robustness has come up, and particularly in the last few years, has been with respect to how sensitive the measure one uses of, say, returns is to one's assumptions about the distribution of returns. This has come up a lot in the context of discussions about fat tails and risk models that were based on assumptions of normality, and when in fact the distribution of stock returns was, over the long run, was more fat-tailed, and therefore the probability of an outlier, in the case of 2008, a negative outlier, was much larger than the risk models had predicted. So the use of robust methods with respect to how sensitive they are to the probability distributions that are assumed has come up a lot the last few years in that context.
Yeah, absolutely, Andrew. And so if you could, for those of you who are listening, if you could take what Andrew said and multiply it by 1,000,000, that's your average Monte Carlo model.
Yeah.
And so when you're thinking about these things, just be aware that these things are very sensitive. And whatever you do, do not do not buy any software based on its promise of robust Monte Carlo models, because that's just not it's not a good reason to spend your money. To tell you the truth.
So,
Okay, mute me again.
okay, yeah.
Is there anybody using Monte Carlo for the trading investigation, Steve? That's actually a very good question, Steve. I was actually recently at the R in Finance, I believe it was in March. I was in the R Finance conference, and I was talking to a hedge fund manager who was commenting on how they were using a certain R package that involves a lot of parallelizations that I'm sure Brian knows a lot more about. And he was mentioning about how he's going through this complicated system and using Amazon to quote-unquote rent cores to do their simulation analysis. And I actually asked him, well, why are you spending all this money? Why are you creating these complicated systems? And he had a very good answer, is that what they were using it for was for mortgage-backed securities. That is, when you have securities that are literally collateralizations of all these different mortgages that are distributed across the country, their concern particularly was credit risk and interest rate risk. That is, what would be the value of this instrument if these two parameters, that is the credit risk or the interest rate risk, change. And how they use Monte Carlo methods for trading was that they would create a relative ranking of these various mortgage-backed securities, and they would use that ranking relative to the prices they saw in the market to decide what to buy. That is, if they saw that, for instance, one mortgage-backed security was priced really, really low, but based on their ranking analysis was actually even low or relatively lower, then they would actually buy it. Or, sorry to put it more succinctly, if the price was really, really high, but they thought that it was really, really risky, they would avoid buying those mortgage-backed securities. And the reason why they got into all of this was because, as I'm sure you know from Bloomberg and other sources, the U.S. is still trying to clear a lot of these mortgages, and there's still a lot of uncertainty as to a value of a lot of these securities that are floating around. And so what this hedge fund was using Monte Carlo systems for was to create a relative ranking or a proxy for how they can understand the risk of these mortgages. But at the end of the day, the price that they paid was actually a market price. That is, these models didn't, while they gave them a price, they weren't really using that price to determine how they would bargain with the trader. What they would do is they would do their analysis, and by the way, in reference to earlier parts of my presentation, this is a system that's very observable. That is, people default or they don't default. Where they locate within the country is very stable, And the actual risks that are building into these mortgage-backed securities are credit risk and interest rate risk, and how those risks create the changes in the value of the mortgage-backed security are actually very observable and very tangible. And that's really how they would use those systems for trading. Did that give you an idea, Steve, of how it would work in practice?
Steve? Actually, you just followed up with something about the robustness.
Again, Steve, with respect to robustness, these words are very rich, and they have a lot of definitions, and they're subject to multiple interpretations. And don't take my definition or how I've laid it as the final word, and by all means, feel free to investigate others. What I try to stick to is things that I understand that are easy for me to communicate. But if there's a richer, if you have a richer source as to what helps you understand what robustness is, by all means, I encourage you to look for it, especially within context.
So, Steve, have both your questions been asked or answered about who's using Monte Carlo? It's for myself. I'm actually building a new high-frequency trading system right now, and I would say 75% of it's all parallelization and done in C++ with R, doing the scripting, and as far as I can tell you, Monte Carlo is going to be a good crust of it. So I don't know if you want. Do you want me to unmute you and see if you want to chime in at all? Just let me know via the chat. If not, how much more do you have, Alan?
That's it, actually.
Was it? Okay.
Yeah, that's it.
Why don't we do some more further questions? Anybody else got any other questions at all? Maybe Steve, if he wants to get into more specifics, or anybody? Just type them out in the chat. We can unmute people as we get to them. Anybody? Wow, we must say. Oh, here we go. Yeah, we could definitely do that, Steve. Yeah, and Gord asked if we're going to be posting this. Yeah, I'm currently recording this, and this will get posted on YouTube. I found a way to do that.
Oh,
so.
and by the way, I'll be on my YouTube channel, which Brian has the link to on his site, and you can find out at my website. I'll be creating a rendition of this that's a bit more filtered, a bit quicker, and a bit more stylized. That will be on YouTube at some point in the future. So hopefully we'll get to that. But that's definitely coming.
Go ahead. There's another couple of questions.
Sandra, are there any examples of how people use in trading? To make money, Sandra? Honestly, no, not that I know of. That hedge fund example is the only example I knew of people actually using Monte Carlo models to make money. Usually what it's used for is risk management purposes. That is, trying to find out the relative risk of various positions so that you can figure out capital allocation decisions. But I'm not aware of anyone who actually uses them to make money for the reasons that I outlined, including sensitivity, complexity, and so forth. That these really aren't designed for real-time results from an aggregate that is really, really complex. I mean, if you think about it, for something simple, let's say the price of Apple, there are literally millions of discrete actions occurring all over the world constantly that determine the price of the Apple stock. And to be able to model that with Monte Carlo simulation is just not possible. It's just intractable, even theoretically. And so it's just they're just not meant for trading per se. That being said, there are many business applications of Monte Carlo methods, and they're much more extensively used these days. And I'm actually it's actually very heartening that these methods are gaining very wide acceptance among the business community.
So CWK said that it's being used in risk management in his country.
Yeah, absolutely, and that's generally been my experience, especially with very large institutions, that they'll generally relegate it to governance measures such as risk management or compliance, and it's usually not incorporated into the profit-generating mechanism. For very small groups such as hedge funds and prop firms, they will use it, such as the example of MBSs that I mentioned. But even then, they're using it on a very very specified case with people who really, really know what they're doing. I mean, these people are really are experts in Monte Carlo modeling for mortgage-backed securities. This is what often these people were doing this for years at banks before they even began to do it at a hedge fund. And so that's really the bar that you're set at for trying to make money off of these things.
Just two things for Steve. I just put up my email address. So if you got any questions one-on-one, you can just email me at that address at feedback@quantlabs.net.
Andrew asked, are there any examples of assessing country risk with Monte Carlo models? Not that I'm aware of, simply because there's so many factors that go into countries or into, I believe you're mentioning currency and government bonds. Generally, for those sorts of levels of analysis, it's scenario analysis is often used. That's what's used by Basel and by the IMF and other major risk institutions. Is that they'll choose scenarios that they think are very bad scenarios based on historical or academic observations, and then they'll pretty much plug these scenarios through these systems to find out where the weaknesses lie. Because it's so hard to observe, because each scenario is so complex and so unique, that Monte Carlo methods are really not designed to be able to replicate that, because Monte Carlo methods are incredibly data hungry. And a good rule of thumb is the simpler it is and the more numbers there are, the better it is for Monte Carlo. If the opposite is true, then the worse it is. And in the extreme case of country risk, you might have 5 observations, and it's going to change next year. And in that case, you just can't use Monte Carlo for that kind of stuff. That being said, for more subsets of risks, such as, let's say, sovereign bonds, and they want to measure interest rate sensitivities, then in those cases, Monte Carlo analysis can be used to know how much capital a trader might need when they're doing market making.
I know, Andrew, also that I've seen on r-bloggers.com, I've seen some examples of some R scripts that do that as well. They're not using specifically Monte Carlo, but as the data gets more advanced and more into the millions, obviously that's where the Monte Carlo kick in. So just go to r-bloggers for any examples of the R scripts. Yeah, I think is it r-bloggers.com?
I don't remember. If you Google it, you'll have to.
Yeah, it's pretty standard R scripting examples. Any other questions at all? We've had a couple of people already drop off, so that's a sign of something there. Anybody other got any questions? Just type them up if you do. If not.
All right, so I guess we'll sign off then. Thanks everyone for coming, and it was great to have you. And Brian, do you want to talk about what's coming up next?
Yeah, I do have a number of coming up future announcements. Actually, I have our next presenter next week online, Mark, who runs a new data service company. I'm not sure if Mark wants to do a general 2-minute little blip on what he's presenting. If you want to just type up an answer, Mark, if you have the capability. Okay, I'll unmute you right now, Mark. Go ahead. Go ahead, Mark. You online? If you want to give a description of what you'll be describing next week. I don't know if Mark's there. Mark, you're unmuted. You okay, Mark?
Thanks, Brian.
Oh, no problem.
Yeah. Thanks for the presentation, Alon. It was very interesting. Yeah, next week I'll be talking and just giving an overview of the startup that we've launched, and that we're going through a couple of phases now of releasing first the free trial and then some of the products and services. So we'll give an overview of the different products and how they would be used or how they're intended to be used in trading applications. Whether those are high frequency or back testing or sort of risk analysis or auditing of order executions. So yeah, fairly high level overview, and just to discuss what the different products are targeted at.
Have you gone actually into production yet, like officially? Because I know you're still kind of in beta, aren't you?
Yeah, so at the moment I think you'd say we'd be classified as being in the beta stage. we'll be releasing the free trial. We're aiming to have that for the AWS reInvent service, sort of conference that's coming up towards the end of this month. And then from there, things should sort of roll out according to the level of user demand for the different services that you can sign up for.
Well, there's always a good demand for good data, that's for sure. Never goes away.
Oh, yeah.
Also, thanks, Mark.
Okay.
Just wanted to let everybody know December 11th is going to be a big day. We're going to have probably one of the best quant guys on the planet doing a presentation on his, how back testing he has issues with it. It's Dr. Ernie Chan, who's not too far away from me. I'll be picking his head a few days later on some stuff as well. He's easily one of the most knowledgeable guys that I've come across in this field, and I'm hoping to get some other guys as well coming aboard, do some other presentations. So that's pretty well it from my end. Ellen, do you have anything else to say? I got to say, I love learning stuff from you, man. It's really helpful.
No, absolutely. I covered everything I want to, and actually I really look forward to the next presenter. They sound like a really interesting bunch.
Yeah, we're trying to line them up. I'm trying to actually get Dirk, who's the developer of RCPP, which is pretty well.
Really?
Yeah,
wow.
I'm hoping. Yeah,
that's almost celebrity status in this world.
Yeah, he's huge. The thing is with him, just so people know about the field of high-frequency trading, there's a huge talk on right now where FPGA and all that, with the advancement of ours, so it's just moving along so fast that there was an announcement, I don't know if you've heard this, Alan, where somebody was just put up an R package about how it can handle up to 12,000 cores online. It's some huge developments within R, and with this C++ bridge now, with RCPP, it's just making the stack between C++ and R becoming the next buzz, I guess, in the world of high-frequency trading. So it's exciting stuff over the next few months. Anybody else got anything to say? I can unmute anybody, or if anyone wants to add comments or anything. Just type away if you want to.
Oh, by the way, for Mr. Chan, are you going to be in the same room or
no, same idea as what you're.
Oh, okay, because I was going to mention you said you were going to pick his mind out.
Oh no, that
if you're meeting up or something.
Yeah, I'll be meeting him one-on-one locally to him.
Right.
So he's going to be a really good resource to have from an algorithmic side, because he's been doing.
Oh yeah, no,
years.
absolutely. I was just going to mention that I'm sure some local users would appreciate that if you were interviewing him, to be there, right?
Yeah, no, this is more some proprietary stuff as well. So.
Oh, okay.
Yeah, but he's already contributing quite a bit. Like, you have to understand, this month is very busy for him. He's actually
it's busy for us all, absolutely.
No, he's actually traveling like to Hong Kong and Switzerland, doing all these courses and stuff. He's like really sought after for his skills. Yeah, it's quite good. Anybody else got any questions or anything at all? This was a really good presentation, really good high level of Monte Carlo. It's awesome, Al. Great job. Anybody else?
Oh, by the way, the slide deck will be on my website. It's just alonhonig.com.
Yeah.
Not now, but it should be out pretty soon. So if you ever want to pick around at it or use it for your own presentation, feel free.
If you want, I can also put it onto the meetup. And actually, I just opened up 2 accounts for slideshare.net as well as scribd.com. So it's really good exposure to get your documents out there. So if you want, you can just throw it my way, and I can put it on.
I don't think our listeners need to hear about our details.
Okay,
so,
no problem.
All right, thanks, guys, and we'll talk about it later.
All right,
All right,
sounds
have
good.
a good night.
Thanks. All right, have a good night, guys.